On the topic of quantified statements, universal statement and existential statement. Before we begin talking about these two statements, let us introduce the concept of predicate. A predicate is a sentence that contains a finite number of variables and becomes a statement when specific values are substituted for the variables. It has a domain, which are the possible values that you can plug into the statement for your variable. It might be true or false. At this point, we are not really worried about the truth and falsity of the statement. For example, P of X is the predicate that's saying that, hey, X squared is always more than X. The domain given to us is R, the set of all real values. Consider P of 2, P of a half, P of negative a half. Which one is true? Which one is false? Well, if you plug in 2 for X, you get 2 squared, which the predicate says must be more than 2. Well, 4 is more than 2. So this statement is true for 2. What if I plug in a half? I'm going to still get a correct and true answer out of it. It says a half to power 2 must be more than a half. Or it says 1/4 must be more than a half all the time. Well, this is a false statement. Another number, which is negative a half, if you plug in negative a half into this statement, you get 1/4, which is more than negative a half. This is a true statement. So you're going to say that this statement in general is not a true statement because we can find a counterexample for it. You can have more than one variable, like 2 variables here. Consider the predicate R of m and n. That's saying that if m is a factor of n squared, then m is a factor of n. The domain of both variables are z or the integers. This statement in general is not a true statement because we can find counterexample like 25 and 10. 25 is obviously a factor of 10 squared or 100, but 25 is not a factor of 10. You can find other examples. It doesn't have to be 25 and 10. You can find other values and show that this is not unique. So there are other counterexamples. Like what? Like, well, you can plug in 8 for m and n for. So 8 is indeed a factor of 4 squared or 16. There is no issue there. 16 can be written as 2 times 8, but 8 is not a factor of 4. So the second part of this statement is not satisfied. So this statement in general is false. This statement can have true values as well. Like what? If I plug in 5 and 10, indeed 5 is a factor of 10 squared or 100, and 5 is a factor of 10. There is no issue there, but since you can find counterexamples, the values that make this statement to be false, this statement in general is not a true statement. Consider the following predicate. If x is less than y, then x squared is less than y squared. Let us take a look at the domain. The domain given to us is R, all real numbers. Is this a true statement? For any x less than y, can you check? Can you say for sure that x squared is less than y squared? Well, we can find counterexample. Like what? If I plug in -2 and another number like 1, so -2 for x and 1 for y, this makes this statement to be a false statement. This is a counterexample because -2 is less than 1 for sure, but 4 is not less than 1. So you found a counterexample. And this counterexample for this conditional statement is not unique. You can find other counterexamples as well. You can come up with many, many examples yourself. For example, if you take x to be -1 and y to be 0, indeed -1 is less than 0, but 1 is not less than 0. So this conditional statement is a false statement in general. Of course, you can find values that satisfy this statement, but since you have at least one example that make this statement to be a false statement, this statement is false in general. For example, if you plug in 3 and 8, indeed 3 is less than 8 and 9 is less than 64. But it doesn't mean that this statement is true all the time. We found two counterexamples that we represented here. If P of X is a predicate and X has a domain like D, we can define the true set of the predicate, which is the set of all values that make this statement to be a true statement. So this true set is a subset of the domain. We denote this by the set of all X values in the domain such that it satisfies P of X. Now, please note that domain D is very important. If we change the domain, we get a different true value. For example, let Qn be a predicate that says n is a factor of 8. Find the true set of Qn if the domain is positive integers. Well, in that case, for positive integers, 1 divides 8, 2 divides 8, 4 divides 8, 8 divides 8. All of these numbers are the factor, or basically are the numbers that divides 8. When you divide 8 by each one of these numbers, you get remainder 0. If I change the domain to be just Z, it means that all integers, you include positive, negative numbers as well. So the factors of 8 are now plus minus 1, plus minus 2, plus minus 4, and plus minus 8. So now that you change the domain from positive integers to integers, we see a change in the true set as well. Question says, find the true set of each predicate here. The very first predicate says, hey, you're going to divide 6 by D, and this number is going to be an integer. And the domain is given to you as Z. So basically, you are dividing 6 by D, and the remainder must be equal to 0. So the true set are basically all the factors of 6 plus minus 6 plus minus 3 plus minus 2 plus minus 1. But if I change the domain, for example, to positive integers, this true set becomes smaller. Just positive numbers are included. Let's take a look at another predicate. It says x squared is in between 1 and 4 inclusive, and the domain is R. In that case, the true set is in the form of an interval, union between two intervals, -2 and -1, union to 1 and 2 inclusive. However, if I change this domain to be just integers, the number of values that satisfy this statement are going to be different as well. The true set includes -2, because -2 to power 2 is less than or equals to 4. It includes -1. If you plug in -1 here, -1 squared is going to be 1, which is more than or equals to 1. If I plug in 1 here, the same. And if I plug in 2, we get 4, which is less than or equals to 4. So see a change in the form of a true set if I change the domain from R to Z. So now that we talked about predicate, let us talk about universal and existential statement. Suppose Qx is a predicate and D is the domain of X. A universal statement is a statement of the form for all X in domain D, Qx. It's going to be true if and only if this statement is true for every single X in the domain D. It is false if and only if you can find at least one X value that makes this false. The value of x that make this statement to be false statement, as we mentioned before, is called a counterexample. Let's take a look at one example here. I'm giving you a predicate to be for all x in domain D, x squared is always more than equals to x, and I'm just restricting the domain to be 1, 2, 3, 4, 5. This statement is a true statement. Why is that? For every single value in the domain, like 1, like 2, like 3, 4, and 5, this inequality proved to be true because 1 squared is more than equals to 1, 2 squared is more than equals to 2, 3 squared is more than equals to 3, 4 squared is more than equals to 4, 5 squared is more than equals to 5. So this universal statement is true when the domain is like this. If I change the domain, then I get different answers. It might not be true all the time. Let Qx be a predicate and D be the domain of X. An existential statement is a statement of the form there exists a value in domain D such that Qx is the statement that you have. This is a true statement. If is defined to true, if and only if Q of X is true for at least one X in D. It's false if and only if Q of X is false for all X in D. So we need to check every value in the domain. Take a look at the following statement. Consider the statement to be there is a positive integer such that m squared is equal to m. So we're looking for just one value that makes this statement to be true statement. As you guessed, we can use just 1. 1 squared is equal to 1. So we found that value that make this statement a true statement. So this existential statement is true in general.